Okay, very good afternoon, my dear students. Today we can discuss the capacity of various discrete channels. Okay, first of all, let us know the basic explanation, or you can say the basic definition of channel capacity, and then we can continue the calculation of channel capacity for various discrete channels, and one analog channel we'll discuss, that is the Gaussian channel. So capacity of discrete channels will be evaluated first, and then we can evaluate the channel capacity of a Gaussian channel. And we'll discuss the bandwidth SNR trade-off in this module. This is the last module of your 4th chapter. So actually this capacity of Gaussian channel is stated by Shannon-Hartley. Already I told you this statement in the last class. So capacity of Gaussian channel is stated as C is equal to bandwidth into log 1 plus SNR base 2. So that is stated by Shannon and Hartley. Two inventors stated the capacity of Gaussian channel, that is Shannon and Hartley. So it is called as Shannon-Hartley theorem, which is the C is equal to bandwidth into log 1 plus SNR base 2. Okay, similarly we will calculate the capacity of several discrete channels. We'll read all those things in the as we can say that properties of discrete channels. So we can discuss as a property, but in the exams they will ask you to consider particular channel, and they will ask you to calculate the capacity. Okay. So already I told you this point in the last class. Shannon, what he stated? He stated that information rate is always less than or equal to the channel capacity. Information rate is always less than or equal to the channel capacity. Okay. So R is less than or equal to C. And he also stated that channel capacity is defined as the maximum value of mutual information. So maximum value of mutual information is our channel capacity. So already you know the mutual information. So it is defined as an uncertain difference between the uncertainties of the priori probability and the posteriori probability of the transmitter section, or can be of the receiver section. So if it is transmitter, it will be I of xj minus I of xj by yk. If it is for the receiver section, it is I of yk minus I of yk by xj. That is the mutual information. So maximum value of the mutual information is defined as the channel capacity. So whatever may be the channel, that may be discrete channel or analog channel, the maximum value of mutual information is stated as the channel capacity C. Okay, and the efficiency is defined as a ratio of mutual information to that of maximum of mutual information. So that is I of xy divided by maximum of I of xy is nothing but the channel capacity. So efficiency you can define it as the ratio of actual trans information I of xy to that of maximum trans information C. So eta is equal to I of xy divided by C. And 1 minus that efficiency gives you the redundancy. So redundancy is defined as a redundancy plus efficiency, the value is generally equal to 1. So redundancy is 1 minus efficiency eta. So eta you can write it as I of xy divided by maximum of I of xy, which is the channel capacity C. Okay, so this is the basic definition for channel capacity, which is the maximum of I of xy. And you can also write the channel capacity as it is always greater than or equal to the information rate. So capacity of a channel should be always greater than or equal to the information rate. So that is stated by the Shannon, and the definition is maximum of I of xy. Let us calculate the channel capacity for various discrete channels first, and then we can move to the Gaussian channel, that is the analog channel. We can list it as a properties. So definition is maximum of I of xy, and it is always greater than or equal to the information rate. Okay, so definition you should write those two statements and the corresponding expressions. stated by the Shannon. These two expressions you need to write as a definition for channel capacity if it was given in the exams. So in exams you may be asked to write the definition for channel capacity and like list the properties of channel capacity, or they may ask you like derive the expression for channel capacity of a noise free channel. Then you have to write everything regarding the noise free channel, which we have studied in the mutual information force property. And first you should define I of xy, and the maximum of I of xy is our channel capacity C. So the whole thing you need to calculate. So we exams lo adutar ella adutarante calculate or derive the expression for channel capacity of a noise free channel. So for a noise free channel, first you need to represent the like model of channel, how the channel appears. And what about its conditional probability matrix? That is receiver data knowing the transmitter, or transmitter data calculating transmitter data knowing the receiver. Okay, so let us move to the properties of channel capacity. Okay, so here first property is for a noise free channel, channel capacity we need to calculate. So the definition is it is equal to maximum of I of xy. So you can write it as maximum of h of x minus h of x by y, or h of y minus h of y by x. So channel capacity C is equal to maximum of I of xy. So which is maximum of h of x minus h of x by y, or h of y minus h of y by x, because you know that mutual information I of xy is can be written in terms of entropies. Okay, entropies, this is the marginal entropy and these two are the conditional entropies. Okay, so C is equal to maximum of I of xy. So it is equal to maximum of h of x minus h of x by y, or h of y minus h of y by x. Okay, so let us define the conditional probability matrix. So conditional probability matrix for a noise free channel, already I stated this in the mutual information. So it is always unity diagonal, because here x1 y1 x1 y1 probability is maximum, because no data from x1 will move to y2 or y3 or y4 up to so on ym. So similarly, no data from x2 will reach y1, y3, y4 up to so on ym. So x2 data will be received by y2 only, and similarly x1 data will be received by y1. Similarly, xm data will be received by ym. So it is in the form of, it is a noise free channel whose conditional probability matrix is in the form of unity diagonal. So you can observe x1 y1 location is the value of x1 y1 is 1 and others are a 0, and x2 y2 will exist and all others are 0 in the second row. Similarly, in the last row only xm ym will exist. Only xm ym will exist. So matrix size is m by m, because it has m elements on the transmitter and m elements on the receiver side. Okay. Now for a noise free channel, h of x by y is equal to h of y by x is 0, because entropy. So if we have a multiple number of messages and if only one message has a maximum property, like maximum probability, then its entropy h of x by y or h of y by x is 0. Okay, so for a noise free channel, h of x by y or h of y by x is 0, because already I told you the property of entropy. Second property. So what is the second property? If you have multiple messages and if only one message has maximum probability and all other message probabilities are 0, then its entropy is 0. So h of x by y is, h of y by x is equal to 0. Therefore, we can say that because these two are 0, I of xy will be either h of x or h of y. Okay, so the same thing I proved in the mutual information. You can see the corresponding slide here. So if you go through the module 4, here you can see. the property. I told you and proved that I of xy is either h of x or h of y. Okay, so the same thing I have used here. So I of xy is either h of x or h of y. So channel capacity, what is the definition for channel capacity? Maximum of I of xy. So maximum of I of xy. It is equal to maximum of h of x or maximum of h of y. So maximum of h of x is log m base 2 and maximum of h of y is log n base 2. Okay, so C is equal to maximum of either h of x or maximum of h of y. So we know that the maximum value of entropy occurs for equally likely messages occurs at P is equal to 1 by m. Then it is log m base 2. Then the entropy is log m base 2 for the transmitter and log n base 2 for the receiver. Okay. You can see here log m base 2 or log n base 2. So that's why what is the first property? For a noise free channel, channel capacity is either log m base 2 or log n base 2 because I of xy is either h of x or h of y. Okay. Now, let us move to the second property. So, second property we are considering the independent channel. So, for an independent channel, I told you for an independent channel the joint probability is equal to joint probability P of xj comma yk is equal to P of xj into P of yk. So, the same I stated in the module 4. So, here you can see. So, I told you the mutual information for an independent channel is 0. Okay, so P of xj comma yk is, it is given as a matrix and like the transmitter side you have m elements and receiver side you have m elements. So, matrix size is of m by m. Okay, and joint probability is equal to product of individual probabilities of transmitter and receiver. So, P of xj into P of yk. So, here what is the other point that I told you? Here either the row elements are equal or column elements can also be equal. So, all the row elements are equal or all the column elements are equal. So, if you observe in this case, x1 is same. Okay. So, here you can see the like first column, first row, x1 row. So, p1, 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 all the probabilities are same. The same you can observe by using the channel shown here. So, the probability of x1 row is p1, p1, p1 to all of the receiver elements. So, p1, p1, p1 up to so on. So, all the probabilities of each and every row independently are equal. If you observe the second row, p2, p2 same value. If you observe the last row, mth row, so probability is pm. So, here either all the row elements are equal or all column elements are equal. In this example, we consider that row elements are equal. Okay. So, what is the, I told you on the day that by using Bayes theorem, we can replace P of xj, xj comma yk as P of xj into P of, P of yk into P of xj by yk, and here joint probability is product of P of xj and P of yk. So, are into product తీసుకుంటారు and here yk gets cancelled and you will get P of xj by yk as P of xj and P of yk by xj as P of yk. So, we used this expression and finally we obtained h of xy, h of x by y as h of x or h of y by x as h of y. Okay, so this property we studied in the 4th module. Okay, let us move to the present PPT. Okay, 6th module 6 PPT. So, where here for an independent channel, what we are considering, mutual information I of xy is 0, because in this case, if you consider the independent channel, here h of x will be h of x by y. or h of y will be h of y by x, because the P of xj matrix is equal to P of xj by yk matrix, and the P of yk is equal to P of yk by xj, because by using the Bayes theorem and the independent probability joint probability relation as P of xj into P of yk, you will get P of xj is equal to P of xj by yk, and P of yk is equal to P of yk by xj. Okay, so like this, if here you can observe h of x is equal to h of x by y, or and h of y is equal to h of y by x. But what you can say here, mutual information is either h of x minus h of x by y, or h of y minus h of y by x. So therefore, mutual information for an independent channel is 0. But from the definition of channel capacity, so what is the definition for channel capacity? Maximum of I of xy. So I of xy is 0. So maximum of 0 will be 0 only. So channel capacity of an independent channel is 0. So capacity is nothing but the mutual information. Okay. So for a noise free channel, channel capacity is C. So how much you obtained? It is either log m base 2 or log n base 2. Please remember the points. For a noise free channel, capacity is either log m base 2 or log n base 2. If you consider the transmitter, it will be log m base 2. If you consider the receiver, it is log n base 2. Because C is maximum of I of xy. And for an independent channel, mutual information I of xy is 0. Therefore, channel capacity will be 0. Because for an independent channel, the marginal entropy is equal to the corresponding conditional entropy. So h of x is h of x by y, or h of y is h of y by x. Therefore, I of xy will be 0. So channel capacity, if you take which is a maximum of I of xy, you will get it as 0. So this is for the independent channel. So these two properties actually somehow we discussed in the mutual information, 4th and 5th properties. So capacity of noise free channel is log m base 2 or log n base 2, and capacity of an independent channel is 0. Okay. Now let us move to the new concepts. Symmetric channel. So let us clearly check, please listen carefully. Here a channel is said to be symmetric. A channel is said to be symmetric when the elements, so third property of channel capacity. Here we are considering the symmetric channel. So a channel is said to be symmetric when the elements of each row or column, when the elements of each row or column are independently identical. Independently identical. So elements are identical, but there is no need that they are in the same order. Okay, so when you can call a channel as symmetric channel, so you can call a channel as symmetric channel when the elements of each row or column, are independently identical. So please all of you observe the matrix shown here. The conditional probability matrix P of y by x, at knowing x, you are calculating the probability of receiver, and knowing the receiver, calculation of probability of transmitter. So conditional probability matrix is equal to, a matrix here is given, and they are telling that this is a symmetrical channel. Here if you observe the row 1 elements, it is 1 by 2, 1 by 4 and 1 by 4. And row 2 if you observe, it has 1 by 4, 1 by 2 and 1 by 4. So here 2 1 by 4s are there, and 1 by 2 is there. Similarly, if you observe the third row, 2 1 by 4s are there, and 1 by 2 is available. Okay, so P of y by x, how you can say that this is P of y by x matrix? What is the rule here? How can I say that this matrix is P of y by x? Can any one of you tell me? So I am writing this matrix, this channel as P of y by x matrix. Or I am also telling that this is P of x by y matrix. Can any one of you tell me how can this matrix be a P of y by x matrix?
Ma'am, even if we interchange the rows and columns, the matrix will be same, ma'am.
Yes. Here I am telling you that this matrix is P of y by x. Okay. So what is the rule to say that, or I can say, what is the condition to say that this matrix is P of y by x? In the module 5, I think I told you there are several conditions to state the matrix as a joint probability matrix or matrix as a specific type of conditional probability matrix. So the rule is that if sum of all the elements present in the matrix is equal to 1, it is joint probability matrix. Okay. If you observe each row here, so row are 1 by 2 plus 1 by 4, 1 plus 1 by 4. If you add the row elements, it is 1, first row elements. Alane, if you add the second row elements, it is also 1. Third row elements, it is also equal to 1. So the matrix is said to be conditional probability matrix P of y by x if the sum of all the elements present in each row is equal to 1. Here first row, if you add all the elements, it is 1. Second row add chesna kuda you will get it as 1. Third row you will get it as 1. So then I can say that it is P of y by x matrix. And what is the condition for P of y by x by y matrix? A matrix is said to be conditional probability matrix P of x by y when the sum of all the elements in each column is 1. In each column is 1. If you take column 1, so it is 1 by 2 plus 1 by 4, 1 by 4. So it is 1. So if you observe the second column, it is 1 by 4 plus 1 by 2 plus 1 by 4. It is also 1. And if you observe the third column, it is 1 by 4 plus 1 by 4 plus 1 by 2. It is also 1. So that's why this matrix can be either P of y by x or P of x by y. So matrix is said to be conditional probability matrix P of y by x if the sum of all the elements present in each row is 1. And a matrix is said to be P of x by y matrix when the sum of all the elements present in each column is 1. Okay, ma? Okay, this is the basic definition or basic rule to state the corresponding type of matrix. Now coming to our symmetric channel. In the third property, we are telling the symmetric channel. A channel is said to be symmetric when the elements of each row or column are independently identical. So if you consider any row, so 3 rows are there. First row has a single 1 by 2 and double 1 by 4s. And the same is repeated for the 3 rows. Okay, so elements of each row are independently identical. I cannot say that these three all are in same order. But in the first row it has 1 by 2, 1 by 4, 1 by 4. If the second row also have 1 by 2, 1 by 4, 1 by 4, then I can say that it is same. But these are independently identical. The elements are identical but not placed in the same order. Okay, then we can say that the corresponding type is symmetric channel. So a channel is said to be symmetrical when the elements of each row or column, any one of the two can be satisfied. So either the elements of each row are independently identical or the columns of so elements of each column are also independently identical. Okay, so C is equal to, so this is this I can say that this is the conditional probability matrix. Can I say that this is joint probability matrix? No, because P of for a matrix is said to be P of xy when the sum of all the elements in the matrix is 1. But here if you add all these, you cannot get it as 1. So that's why this is not at all the joint probability matrix, because the sum of all the elements in each row is 1. Each row, if you take row 1, row 2, row 3. So any row if you take, sum of elements of each row is 1. So I can say that it is P of y by x matrix. And here the sum of all elements in each column is also 1. So that's why it can be P of x by y. Okay. So because the row elements or column elements are independently identical, we have represented as either P of y by x or P of x by y. Okay, good. Next, C is equal to, let us calculate the channel capacity C. What is the definition for channel capacity? It is the maximum of I of xy. Already we know that channel capacity is the maximum of I of xy. So it is equal to maximum of h of x minus h of x by y. H of x minus h of x by y. So maximum of h of x minus what is h of x by y? Here we are representing this which entropy? Conditional entropy h of x by y in terms of average conditional entropy h of x by yk. I think you will remember the conditional entropy h of x by y in terms of average conditional entropy knowing yk. See, while deriving h of x by y, expression for h of x by y, on that day I told you two steps are there. First step is to represent the conditional entropy in terms of the corresponding average conditional entropy. So h of x by y is the conditional entropy of transmitter knowing the receiver events. Now here you are representing this conditional entropy in terms of average conditional entropy knowing yk, that is h of x by yk. So how can you write h of x by y? It is summation k is equal to 1 to n p of yk into h of x by yk, where h of x by yk is the conditional average conditional entropy knowing receiver yk, So I can write h of x by y as summation k is equal to 1 to n p of yk into h of x by yk. Now what is summation k is equal to 1 to n p of yk? So sum of all the elements of an event is 1. So summation k is equal to 1 to n, p of yk is 1. Okay, p of yk is 1. So maximum of h of x minus, I represented this as 1. What we did here, C is equal to maximum of I of xy. Okay, so maximum of h of x minus h of x by y. Okay, please take this. So C is equal to maximum of I of xy. So maximum of h of x minus h of x by y. First I represented h of x by y as in terms of average conditional entropy h of x by yk. So it is maximum of h of x minus, I represented summation k is equal to 1 to n p of yk as 1. Okay, into h of x by yk. So it is equal to log m base 2, because what is the first term? First term is maximum of h of x. First term is maximum of h of x. It is log m base 2. Because I told you x represents the transmitter section event and maximum entropy occurs at p is equal to 1 by m is log m base 2. This is the property of entropy, sixth property of entropy. Okay, so I can write it as log m base 2. First term maximum entropy is log m base 2 minus, replace this summation k is equal to 1 to n p of yk as 1. So if you replace this as 1, you will get only h of x by yk. So what is the channel capacity of symmetric? So what is the capacity of symmetric channel? It is a log m base 2 minus h of x by yk. Okay, therefore for a symmetric channel, the channel capacity is C is equal to log m base 2 minus h of x by yk. Okay, h of x by yk. Please remember this third expression. So third property of third property of channel capacity is, for a symmetric channel, the capacity C is equal to log m base 2 minus h of x by yk, where h of x by yk represents the average conditional entropy of transmitter knowing a yk element. So C is equal to log m base 2 minus, this is the average conditional entropy of transmitter knowing yk event, Okay, so this is all about the third property of channel capacity. Let us move to the fourth property. So in the third property, we discussed the symmetric channel. Symmetric channel where the elements of each row or column are independently identical. Okay. Now for a binary symmetric channel, see here, if you observe the symmetric channel, the matrix size is of 3 by 3. So here there may not be such a case that the matrix size is not only 2 by 2. Okay, so the matrix size here is 3 by 3 or can be 4 by 4 or 5 by 5. But the condition is that elements of each row or column are independently identical. Or can be both. Rendu kuda avvachu. Elements of rows or columns both are independently identical. Now, coming to the fourth property, for a binary symmetric channel, please consider binary symmetric channel. The elements of two rows or the elements of two columns are independently identical. Here only the elements of two rows or elements of two columns are independently identical. So always this binary symmetric channel matrix size is 2 by 2. So for a binary symmetric channel, so it has two elements on the transmitter and two elements on the receiver. So here we are considering the two elements as x1, x2 and two elements on the receiver as y1, y2. Okay, so total of like a transmitter section elements are x1, x2. So m is 2. So m represents the number of elements on the transmitter side. Okay, and n represents the number of elements on the receiver side. N represents the number of elements on the receiver side. So here we have two elements on the receiver side, y1, y2 and two elements on the transmitter side. Okay, so matrix size is 2 by 2. So for a binary symmetric channel, the elements of two rows or the elements of two columns are independently identical. Here it is a matrix size of 2 by 2 because two elements are there on the transmitter side and two elements are there on the receiver side. So the two elements are x1, x2 and two elements on the receiver are y1, y2. So this model of representation of channel is generally called as binary symmetric channel. So binary represents two elements on transmitter and two elements on receiver. And symmetric channel represents that the two elements of the corresponding two rows or two columns are independently identical. Okay, so this is a corresponding binary symmetric channel, and here you can see the corresponding probability matrix. So here we are calculating the probability of Y knowing the receiver X1 and probability of X knowing the receiver Y. So then the corresponding conditional probability matrix is P of Y by X is equal to P of X by Y is equal to. Why and every time I am writing equal? Every time is it valid? No. For a symmetric channel only it is equal. For a symmetric channel, here P of Y by X is equal to P of X by Y, because here the elements are independently identical. Now please carefully observe the matrix. Here what is the probability of X1 to move towards Y1? P. What is the probability of X1 to move towards Y2? 1 minus P. For example, if P is 0.8, what is X1 Y2 probability? 1 minus 0.8. It will be 0.2. Similarly, what is the probability of X2 moving towards Y1? 1 minus P. What is the probability of X2 moving Y2? It is P. So, probability of X1 reaching Y1 is P and X2 reaching Y2 is P. So, probability of the input element in the forward direction reaching to the correct destination is P. And if X1 actually it should move towards Y1, but there exists some probability 1 minus P for X1 to reach Y2, and there exists some probability 1 minus P for X2 to reach Y1. Please listen carefully. So what is the probability of X1 to reach Y1? P. Similarly, what is the probability of X2 to reach Y2? P. And what is the probability of X2 reaching Y1 or X1 reaching Y2? It is 1 minus P. Okay, why this channel is called as binary symmetric channel? Binary represents two elements on the transmitter and two elements on the receiver side. And a symmetric channel represents that the corresponding elements of each row, or you can say the two rows, or the corresponding elements of the two columns are independently identical. Please observe the first row. So we are representing the conditional probability matrices. Please observe first row. First row consists of P as the first element and 1 minus P as the second element. Why I have written like this? Because first element is X1 Y1. First row second element is X1 Y2. And second row first element is X2 Y1. So X2 Y1 probability is 1 minus P. So I have written here. And X2 Y2 is P. So X1 reaching Y1 is P. And X1 reaching Y2 is 1 minus P. And here you can see X2 reaching Y1 is 1 minus P probability. So I have written here. And this is X2 Y2 element. So X2 reaching Y2 is P. So that's why we can represent the corresponding elements in the conditional probability matrix. So it is of size 2 by 2. It is of size 2 by 2. So P of Y by X is equal to P of X by Y is equal to, I mentioned the corresponding elements. So first element is X1 Y1 element, and first row second element is X1 Y2, and second row first element is X2 Y1, and second row second element is X2 Y2, that is P. I think you understood the way of representing the matrix using the channel. So this is a channel given to you, and using this channel you should construct the matrix. So this is not the joint probability matrix, because if you add all these P plus 1 minus P plus 1 minus P plus P, so it will be 2. 2P 2P gets cancelled, but you will get 2. So I cannot say that this is joint probability matrix. What is the condition for joint probability matrix? Sum of all the elements in the matrix should be equal to 1. But if you see sum of elements in the first row, it is P plus 1 minus P, it will be 1. If you observe the sum of elements in the second row, it will be 1 minus P plus P, so it will be 1. Next, if you observe the first column, P plus 1 minus P, so it will be 1. So second column elements add cheyandi 1 minus P plus P, it will be 1. So like that you can represent either as P of y by x, because sum of elements in the row is 1, and you can also state it as P of x by y, because sum of elements in the column, in each column is 1. Now channel capacity, let us derive the expression for channel capacity for a binary symmetric channel. So the short form representation is BSC, binary symmetric channel. So we know that channel capacity C is defined as maximum of mutual information. I took the same expression, and it is equal to maximum of, what is the representation of mutual information in terms of entropies? So we can write it as h of x minus h of x by y. Okay, so h of x minus h of x by y, you can also write it as h of y minus h of y by x, no issue with that. So it is equal to maximum of h of x minus, this is the conditional entropy. I told you in the symmetric channel that represent this conditional entropy in terms of average conditional entropy h of x by yk, knowing yk. So I have represented h of x by y as summation k is equal to 1 to n p of yk into h of x by yk into h of x by yk. So here maximum of h of x is how much? Already you know, maximum entropy is log m base 2. So I have written as log m base 2 minus h of x by yk. What is h of x by yk? Average conditional entropy of transmitter knowing a yk element. Because here we considered sum of all the elements in the yk, or you can say sum of elements, sum of all the elements of the transmitter will be, of the receiver will be 1. Sum of all the elements on the receiver matrix is 1. So that's why I can replace summation k is equal to 1 to n p of yk as 1. Okay, so it is log m base 2 minus h of x by yk. So that is log 2 base 2 minus h of x by yk. So it is log 2 base 2 is how much? Why m is 2? Because this is binary symmetric channel. 2 elements on the transmitter and 2 elements on the receiver. Okay, so log m will be 2 and also n will also be 2. So log 2 base 2, or n is also 2, log 2 base 2. So log m base 2 minus h of x by yk. So it is log 2 base 2 minus h of x by yk. Okay. So it is log 2 base 2 is how much? It is 1. And h of x by yk, h of x by yk is the average conditional entropy. Now, let us see what is the general representation of average conditional entropy. So, for fixed yk, so if yk is fixed here, what is the expression for average conditional entropy? H of x by yk. See, these 2 points I stated you, these 2 points, what are the 2 points? One is representation of conditional entropy in terms of average conditional entropy, and the second one is representation of average conditional entropy. These 2 points I stated while deriving h of x by y. Okay, so h of x by yk. So the equation for h of x by yk is so for fixed yk, the average conditional entropy h of x by yk is minus summation j is equal to 1 to m minus summation j is equal to 1 to m p of xj by yk into log p of xj by yk base 2. So it is minus summation j is equal to 1 to m p of xj by yk log p of xj by yk base 2. So this is the expression for average conditional entropy. So just I represented the expression for average conditional entropy. So in the channel capacity expression. Therefore, the channel capacity is 1 minus of minus summation j is equal to 1 to m. M value is 2 here. Because here 2 elements on transmitter and 2 elements on receiver. So transmitter side is m. So m is 2 here. So minus summation j is equal to 1 to 2 p of xj by yk. Same expression I have written here. Into log p of xj by yk base 2. First ఏం చేసామమ్మా, first we represented h of x by y in terms of average conditional entropy, h of x by yk. Next I have written average conditional entropy expression as minus summation j is equal to 1 to m p of xj by yk log p of xj by yk base 2. So this is the definite equation for average conditional entropy. Okay, so you will get, you can, so it is 1 minus, I represented h of x by yk in the channel capacity expression by replacing m as 2. So here minus of minus you will get it as plus. So the same expression I have rewritten here. So 1 minus of minus summation j is equal to 1 to 2 p of xj by yk log p of xj by yk base 2. So this is the elements, these are the elements of the corresponding matrix. Here actually what p of xj by yk represents, p of xj by yk represents the p of xj element for a fixed value or known value of yk. So take any one of the column, that can be column 1, that is first column, or second column. Take any one of the column. You can take either the first column or the second column, that's your wish. So I took the conditional probability matrix for a particular column, that is knowing yk, because this is the expression for channel capacity C which we obtained for the binary symmetric channel. So take the conditional probability matrix either p of x by y or p of y by x, which we have defined in the earlier slide. So last slide I defined this probability matrix. Let us solve the h of x by yk using this matrix. Because probability matrix is known to you, please substitute in this elements in the average conditional entropy to calculate the channel capacity. Okay, so P of the conditional probability matrix is known to you. Now, in this matrix you can see fix any column because denominator is yk. So, knowing yk or fixing either it as column 1 or column 2. So, you can take either the column 1 or column 2. So, channel capacity of a binary symmetric channel will be 1 minus, 1 minus, minus of minus, so it will be plus, plus take any column, that can be column 1 or column 2. First element into log the same first element, second element into log the same second element. So, for j is equal to 1 at a first row, fix any column, let us fix the first column. First row element is p. So, p log p base 2. Next, Second row element of the first column is 1 minus p. So 1 minus p log 1 minus p base 2. So this is the average conditional entropy. Okay, average conditional entropy of xj knowing yk or fixing yk. So you can fix it as either first column or second column, but you will get the same channel capacity because it consists of same elements p and 1 minus p. Here also 1 minus p and p. So p log p base 2 plus 1 minus p log base 2. For the second column, if you take, it will be 1 minus p log 1 minus p base 2 plus p log p base 2. So both are same. You can take either column 1 or column 2 because you are calculating the p of xj by yk, that is h of x by yk. Okay, so finally channel capacity for a binary symmetric channel is 1 plus, because 1 minus of minus, you can write it as 1 plus p log p base 2 plus 1 minus p log 1 minus p base 2. So here it is 1 minus, can any one of you tell me what is this p log p base 2 plus 1 minus p log 1 minus p base 2? If you clearly observe this matrix, if you clearly identify this matrix, so let us move to the, once again let us move to the channel. Here if you see the channel, h of x represents the entropy of the transmitter. H of x represents the entropy of transmitter. Okay, so it consists of two elements, that is x1 and x2. Okay, if you fix any column, what is the probability? That can be either p log p base 2 plus 1 minus p log 1 minus p base 2. So I can say that the corresponding element, the entropy can be either h of x or h of y. Why h of y? Because if you take any row, if you take any first row, it is the entropy of first row is p log p base 2 plus 1 minus p log 1 minus p base 2. So therefore, channel capacity can be represented as either 1 minus h of x or 1 minus h of y or 1 minus h of y. So, or in terms of expression, you can write it as C is equal to 1 plus p log p base 2 plus 1 minus p log 1 minus p base 2. So we can in a simplified manner, we can write it as 1 minus h of x plus 1 minus h of y. Okay, please note this expression. Channel capacity for a binary symmetric channel. Binary symmetric discrete channel capacity is C is equal to 1 minus h of x by yk. That h of x by yk is obtained by using p of x by y. So fixing any column, you can write the channel capacity as 1 minus of minus. So it is plus p log p base 2 plus 1 minus p log 1 minus p base 2. Because it is a symmetric channel, you can write it as either 1 minus h of x or 1 minus h of y. Please write this statement. So in the third property, we discussed the symmetric channel and we have defined the capacity as C is equal to log m base 2 minus h of x by yk. In the binary symmetric channel, you can write m is equal to n is equal to 2 because it is a 2 by 2 matrix. So log 2 base 2 minus h of x by yk vastundi. So log 2 base 2 is 1 minus h of x by yk. We have written h of x by yk as minus summation j is equal to 1 to 2 p of xj by yk log p of xj by yk base 2. Okay, so just I consider the corresponding probability matrix by yk annaru ante you can take either column 1 or column 2. So knowing the corresponding column, a representation of p of x. So p log p base 2 plus 1 minus p log 1 minus p base 2. or for the second column it will be 1 minus p log 1 minus p base 2 plus p log p base 2. So finally we obtained the channel capacity for binary symmetric discrete channel is 1 minus either h of x or 1 minus h of y. Okay. Please remember these expressions. Now let us move to the fifth property. So what is the fifth property? So in the first property, we consider the noise-free channel. There h of x by y, h of y by x both are 0. So we will get the channel capacity as maximum of mutual information. So it is either log m base 2 or log n base 2. And for second property, for independent channel, we obtained it as 0. Because for the independent channel, h of x by y is equal to h of x and h of y by x is h of y. And what is the third property? For the third property, we considered symmetric channel and we obtained the channel capacity as log m base 2 minus h of x by yk, because summation k is equal to 1 to n, p of yk is 1. And similarly, as a fourth property, what is the fourth property? We considered the channel capacity of binary symmetric discrete channel. What is the channel capacity? C is equal to 1 minus either h of x or h of y. Or you can write in a simplified manner, or by replacing the corresponding probabilities, you can write it as 1 plus, because h of x is once again negative. H of x is minus of p log p base 2 plus 1 minus p log 1 minus p base 2 vastundi. So you can write it as 1 plus p log p base 2 plus 1 minus p log 1 minus p base 2. This is the capacity of binary symmetric channel. Now let us move to the fifth property, so that here you can discuss the binary non-symmetric channel. Non-symmetric. So as the name specifies that these two, the elements of the two rows or the two columns are not independently identical. There is no need for the two row elements or the two column elements as identical. Okay. So for a binary non-symmetric channel, so because it is a binary channel, once again here the number of elements on the transmitter is 2 and the number of elements present on the receiver side is also 2. So here m is equal to 2. So let us consider the two elements as same to that of BSC channel, that is binary symmetric channel. So take the elements as x1, x2 on the transmitter, and on the receiver please consider the elements as y1 and y2. So what are the elements present on the transmitter side? x1, x2. What are the elements present on the receiver side? y1 and y2. Now because this is a non-symmetric channel, there is no need that all the elements are identical. So here P11 is not equal to P12 and P21 is also not equal to P22. So that's why we have considered a different probabilities, not like in the case of binary symmetric channel where we have considered x1 y1 probability as P and x2 y2 probability also we considered as a P. So forward direction we considered the probability as P and in the opposite direction we consider the probability as 1 minus P. But in this case the elements are not equal. So that's why we have considered different probabilities. x1 y1 probability we considered it as P11 and x1 y2 we considered as P12, x2 y1 we considered as P21 and x2 y2 we considered as P22. So 4 probabilities are defined for the following paths: x1, y1, x1, y2, x2, y1, x2, y2. So this is a binary non-symmetric channel. It's shown in the figure. Now let us represent the corresponding conditional probability matrix for the channel shown here. First element is x1, y1 element. What is the x1, y1 element? Please see here what is x1, y1. x1, y1 element is p11. x1, y1 element is, please wait. x1, y1 element is p11. Okay, that's why I have represented here p11. Next x1, y2. x1, y2 is p12. So we have written p12. And second row, that is x2, first column, x2, y1. The probability is p21. Please carefully observe the suffix. So x2 to y1. So I represented as p suffix 21. And for x2 to y2, suffix is 22. Okay, so p22. So this is the probability matrix for the binary non-symmetric channel. Because it is binary, the matrix size is 2 by 2. Because it is binary, the matrix size is 2 by 2. But if you observe the probability values, all of these are not identical because it is a non-symmetric channel. Okay, anyhow, we have using the channel shown here, we have constructed the probability matrix consisting of x1, y1 element as p11, x1, y2 element as p12, x2, y1 element as p21, and x2, y2 element probability as p22. So matrix size is 2 by 2 because it is a binary channel. As it is a non-symmetric, all these elements are not identical. Okay, now let us calculate the capacity of the binary non-symmetric channel. Okay, for a binary symmetric channel, directly we took the expression log m base 2 minus h of x by yk, and we replaced h of x by yk. Okay, we replaced h of x by yk, and finally we obtained it as 1 minus of minus p log p base 2 minus 1 minus p log 1 minus p base 2. So we have written it as 1 minus h of x or 1 minus h of y. That is for binary symmetric channel. But here in the case of binary non-symmetric channel, two auxiliary variables Q1 and Q2 are introduced. Two auxiliary variables Q1 and Q2 are introduced such that the product of P matrix and Q matrix is minus H. So P is a probability matrix and Q matrix is the auxiliary variable matrix, which is a column matrix, and H is the entropy. Okay, so what is the probability matrix? It is P11, P12 on the first row, P21 and P22 on the second row, and Q matrix is Q1, Q2. So it is equal to minus of P11 log P11 base 2 plus P12 log P12 base 2. This is the H of X, entropy of transmitter. P21 log P21 base 2 plus P22 log P22 base 2. So this is the entropy of the second row. So this is the entropy of the first row x1, and this is the entropy of second row, that is x2. Because for x1, if you observe, the probabilities are p11 and p12. So entropy of h of x1 is p11 log p11 base 2 plus p12 log p12 base 2 minus of. Okay. So similarly h of x2 is P22 log P22 base 2 plus P21 log P21 base 2. So negative sign is common for the entropy. So I took a minus as common. So we represented this whole factor as H. Now here you will get two expressions. So one is P11 into Q1 plus P12 into Q2, which is P11 log P11 plus P12 log P12. Similarly, using second row, that is P21 into Q1 plus P22 into Q2 is minus of P21 log P21 base 2 plus P22 log P22 base 2. Here you will get, by using this PQ is equal to minus H equation, by using the product of P and Q matrices, which is equated to entropy, you will get two expressions or two equations. Now you have to solve the Q1 and Q2. You need to solve Q1 and Q2. These two are the auxiliary variables, introduced auxiliary variables. So you can calculate Q1 and Q2 by using the product of PQ matrix as minus H. And using the two equations, let us solve Q1 and Q2. So after calculating Q1 and Q2, the channel capacity is obtained as C is equal to log of 2 power Q1 plus 2 power Q2. Okay, this is a general process. This is a like a process, or you can say this is a procedure for calculating the channel capacity, because the complete variables are not dependent to each other. So because all the probabilities are independent to each other, okay, not identical to each other, we have defined two auxiliary variables. Those two variables are Q1 and Q2. These two are introduced. How these two are introduced? Such that PQ is equal to minus H. If you multiply the probability matrix with Q matrix, so Q matrix is nothing but the two auxiliary variables, which is a column matrix. And if you equate this to the entropy, then you will get two equations. Upon solving the two equations, you will get Q1 and Q2. So two equations are there, and you can calculate two unknown parameters. And using Q1 and Q2, you can obtain the channel capacity as C is equal to log 2 power Q1 plus 2 power Q2. So what is the capacity of binary non-symmetric channel? C is equal to log 2 power Q1 plus 2 power Q2, where Q1 and Q2 are the two auxiliary variables which can be obtained by using a relation PQ is equal to minus H. Okay, so anyhow we can solve the model of problems by using all the properties, but remember the channel capacity expression and the equations which are necessary for solving the problems. You need this equation PQ is equal to minus H and C is equal to log 2 power Q1 plus 2 power Q2. And you should be able to construct the probability matrix by using the channel shown here, because for the first while representing the probability matrix, please see the first row. First row ante x1 related vi chusukovali. First row is x1, so x1 to y1 is p11. So first element is x1 y1 and this element is x1 y2. Next this element is x2 y1 because second row first column, and this element is x2 y2, so second row and second column. So accordingly we will represent the probabilities, and finally we obtained C as log 2 power Q1 plus 2 power Q2. Okay, and let us move to the binary cascaded channel. So this is a this you can say that this is the sixth property of channel capacity. So first one is noise free channel, second is independent channel, third is symmetric channel, fourth one is binary symmetric channel. So at M is equal to N is equal to 2. and symmetric కాబట్టి either the row elements or the column elements are independently identical. And fifth property is binary non-symmetric channel. So because it is non-symmetrical, we have introduced two variables q1 and q2 such that pq is equal to minus h, and you can obtain channel capacity C as log of 2 power q1 plus 2 power q2. Okay, sixth channel is, or you can say sixth property is binary cascaded channel. Now, please listen carefully. This is very, very important, and you will get some model of problems using this kind of binary cascaded channel. Cascaded ante the output of the first channel is fed as input to the second channel. Cascaded, what it mean actually? The output of first channel is fed as input to the, is applied as input to the second channel. But here he said that binary cascaded channel. So two channels are cascaded. Which channels are cascaded? Binary channels are cascaded. Two binary symmetric channels are cascaded here. Two binary symmetric channels are cascaded. So you can write it here. In a binary cascaded channel, two binary symmetric channels are cascaded. Okay. Now, for the first channel, okay, so cascaded ante enti, the output of first channel is fed as input to the second channel. Here let us consider the first channel. Please go through the channel shown here. This is the channel given to you, and what are the inputs? X1, X2. What are the outputs of the cascaded channel? Z1 and Z2. But intermediate, if you observe, another section is also available, that is section Y, consisting of two elements Y1 and Y2. Please listen carefully. Here if you observe this whole cascaded channel, the inputs are X1 and X2, and the output of the whole cascaded channel is Z1, Z2. But here there is an intermediate section Y1, Y2. Ante the output of the first channel is Y1, Y2. And those are fed as input to the second channel, second binary channel. So first channel, for the, here I represented, please see here. For the first channel, input elements are X1, X2. And output elements are Y1, Y2. So input elements are X1, X2 and output elements are Y1, Y2. For the second channel shown here, because cascaded represents that the output of the first channel is applied as input to the second channel. For the second channel, the input elements are Y1, Y2 and the output elements are Z1 and Z2. Okay, now please observe the first channel. Now what is the whole channel? The complete channel is a cascaded channel whereby the output of the first channel, that is Y1 and Y2, are applied as input to the second channel whose outputs are Z1 and Z2. Now the equivalent representation of this binary cascaded channel shown on the left side. Okay, the equivalent diagram is represented on the right side. If you observe the channel shown on the right side, it is the equivalent representation of the cascade of two binary channels shown on the left side. So left side is a left side figure or the channel shows the cascade combination of first channel followed by second channel, and the figure shown or the channel shown on the right side is the equivalent representation, So what is X1? Please observe X1 and X2 are the inputs to the first channel and also inputs to the cascaded channel. What is the complete output of the cascaded channel? Z1, Z2. So that's why I have represented Z1 and Z2 are the outputs of cascaded channel and X1 and X2 are the inputs to the cascaded channel. So X1, X2 are the inputs, Z1, Z2 are the outputs. Okay, now In order to represent the probability of x1 z1, x1 z2, that is the first row elements. Similarly, second row elements x2 z1 and x2 z2. So in order to represent the probabilities, first you should go through the possible directions or the possible path from x1 to z1. Okay. Now please clearly observe the figure shown on the left side. Observe the figure shown on the left side. In order to calculate the probabilities of x1 z1, x1 z2, x2 z1 and x2 z2. Because this is also a binary channel, so equivalent form also represents the binary channel, but it is a cascade of two binary symmetric channels. One is the first channel having inputs x1, x2, outputs y1, y2, and it is cascaded with second channel whose inputs are y1, y2 and outputs are z1, z2. Okay, so now the first channel is cascaded, the output of first channel is fed to the input to the second channel. To represent the equivalent form of binary cascaded channel whose inputs are x1, x2 and outputs are z1, z2. Now we need to represent the probabilities. Now we need to represent the probability matrix. So in order to represent the probability matrix, you need the probabilities of the corresponding 4 elements. So before representing the probability matrix, let us see how many paths are available to move from x1 to z1. Because you need to calculate the x1 z1 probability. So to tell the x1 z1 probability, first you should know the available paths to move from x1 to z1. Because in the first symmetric channel, we consider the x1 y1 probability as p. Forward path probabilities we considered as p. And the opposite path we consider the probability as q. Here q is 1 minus p. Remember that q is 1 minus p. So forward probabilities are p and the opposite probabilities are q. Similarly, y1 to z1 and y2 to z2 probabilities are p and opposite probabilities, that is y1 z2 or y2 z1 probabilities are q. Now I request any one of the student to tell me what are the possible paths to move from x1 to z1. Any one of you, please tell me. I want the probability from x1 to z1. What are the possible ways to move from x1 to z1? We need x1 z1 probability. So in order to get x1 z1 probability, what are the possible paths to move from x1 to z1? So please respond. How can we move from x1 to z1? How the amount of data of x1 can be received by the z1? Cheppandamma. x1 to z1, how many paths are there, intermediate paths? So we can move from x1, we can directly move through the forward path at x1, y1, z1. So this is the forward path. And there is another path where we can move to y2 and from y2 to z1 we can move. So two possible paths are available to move from x1 to z1. Please see carefully. x1, y1, z1. And another path to move from x1 to z1 is x1, y2 and z1. Please see the same I represented in the first point. Probability of signal moving from x1 to z1. Okay, so here two possible paths are there. One is x1, y1, z1. So probability will be p into p. So p square. And probability of x1 moving z1 via y2. So or x1, y2, z1. చూడండి ఇక్కడ x1, y2, z1 అంటే x1, y2 probability is q and y2, z1 probability is also q. So q into q. So total probability is q square. So total probability of the signal moving from x1 to z1 is p square అంటే p into p plus another path is also available, that is x1, y2, z1, that is q into q square. So total probability of x1 moving towards y1 is p square plus q square. So in order to represent the probability of signal moving from one position to other position, first of all you should see the various paths to move from initial position to the required position. అంటే మీరు ఇప్పుడు x1 to y1 calculate చేయాలి. So how many paths are available? First check the forward path, that is p into p. So total probability is a product of the corresponding individual probabilities. And x1, y2, z1 is q into q square. So because two paths are available, the total probability will be p into p plus q into q. So p square plus q square. Similarly, I think you can calculate now from x1 to z2. Can any one of you tell me how many paths are available to move from x1 to z2? Any one of you? x1 నుంచి z2 కి move అవ్వాలి. How many paths are there? x1 to z2. Please respond. చెప్పండమ్మా. How can we calculate the probability of x1 towards z2? Because first row second element is x1 z2. So ఎలా calculate చేస్తారు చెప్పండి? x1 to z2, how many paths are there? Actually, the strength is very poor today. Actually, every day we have almost all 60 students, but now today only 38 students are there. Can I know the reason why the strength is very poor? E1
Ma'am.
Okay, ma'am. Can I tell me how many possible paths are there to move from x1 to z2? I need to calculate the probability of x1 z2. x1
X1
z2.
to Y1 and then to Z2, ma'am.
x1 z2 via y1. Okay, very good. Next.
And via Y2, ma'am.
Via
X1
Y2.
to Y2 and then to Z2.
Very good. x1 to y2 then z2. Now can you tell me the probability of x1 moving z2 via y1.
PQ, ma'am.
P into Q. Okay, very good. Can it know what is the probability of x1 to z2 via y2?
Q square, ma'am.
ఇక్కడ చూడండి x1 to y2 is Q and y2 to z2 is P.
Yes, ma'am. Sorry, ma'am. PQ.
అప్పుడు PQ అవుతుంది. సో టోటల్ ప్రాబిలిటీ ఏంటి? వాట్ ఈస్ ద టోటల్ ప్రాబిలిటీ ఆఫ్ x1 మూవింగ్ టువర్డ్స్ z2 via 2 paths? టోటల్ ఎంత అవుతుంది? PQ సారీ యాక్చువల్గా ఇక్కడ నేను Q స్క్వేర్ పెట్టాను. ఓకే సారీ అమ్మా, ఇక్కడ యాక్చువల్లీ ఐ హావ్ రిటర్న్ దిస్ యాజ్ x1 moving z2, it is pq plus pq kada. Is it okay? Probability of sigma x1 moving z2 is pq plus pq, so it is also pq. So how much it is? Now it is okay, 2 pq. Next, can you tell me the probability of moving x2 to z1? x2 to z1
to y1 and then to z1.
x2 to
y1 and then to z1.
okay, what is the probability?
PQ, ma'am.
PQ. Next, x2 to z1 another way.
x2 to y2 and then to z1, ma'am.
So total probability is PQ. So PQ plus PQ is 2 PQ. Okay, good. Next, can you tell me what is the probability of x2 signal moving z2 towards z2?
Yes, ma'am. x2 to y2 and then to z2.
x2 to y2 and that to z2. What is the probability? P into P. P square. What is the another path?
x2 to y1 and then to z2, ma'am.
x2 to y1 and that to z2. The probability is
Q square.
Q square. So total probability is P square plus Q square. Okay, very good. Thank you very much. You can mute. Thank you, ma. Okay, so finally we have seen a cascaded channel where two binary symmetric channels are cascaded. Okay, so please all of you mute your microphones. All the students, please mute. So I think even muted. Other students, please mute yourself. Okay, good. Okay, so let us see here. Okay, now here you can see for a binary cascaded channels, two binary symmetric channels are cascaded. Okay, so if you observe the a cascade of two channels, so first channel inputs are x1 x2 and outputs are y1 y2, and second channel inputs are y1 y2 and outputs are z1 z2. So for a binary cascaded channel, here two binary symmetric channels are cascaded, and the equivalent form of this cascade of two channels is shown on the right side, and we have defined the probabilities of the corresponding paths from x1 to z1, x1 to z2, x2 to z1 and x2 to z2 upon considering the possible ways of moving from the source to the destination. Here we have two source elements and two destination elements. Two source elements are x1, x2 and two final destination is z1, z2. So we have four possibilities. So x1 can move towards z1, that is the actual path, and sometimes x1 data may move towards z2. So we have represented the corresponding possibilities of paths because it is a cascaded channel. It is not an individual channel. It is a cascade of two channels. So it has to move an intermediate path. So x1 to y1 probability we have calculated by using x1 y1 z1 path and x1 y2 z1 path. So that is p square plus q square. And similarly, the probability of signal moving from x1 to z2. So we calculated using x1, y1, z2 and x1, y2, z2. Okay, so we obtained as 2pq. And similarly, x2 moving towards z1. So x2, y1, z1 and x2, y2, z1. So we obtained it as pq plus pq, so it will be 2pq. Similarly, the possible path of x2 moving towards z2 is x2, y1, z2 and x2, y2, z2. Okay, x2, y1, z2 and x2, y2, z2. Okay, so it is p square plus q square. So finally, we obtain the whole properties like this. Now, please remember what is the probability of x1 moving towards z2? x1 moving towards z2 is 2pq and x2 moving towards z1 is 2pq, opposite probability, opposite way of moving. But in the forward direction, we have written as 1 minus 2pq, that is for x1 z1, and x2 z2 also we have written as 1 minus 2pq, because there exists a relation between p and q. Okay, because the sum of probabilities of an event x1 is equal to 1. So x1 probability in the opposite direction is 2pq. And the forward direction is p square plus q square. And anyhow, this should be equal to 1 minus 2pq, because sum of the probability should be equal to 1. Now anyhow, let us see what is the forward probability, that is from x1 to z1 and x2 to z2. Why instead of p square plus q square, why we have written it as 1 minus 2pq. Let us move to the next slide so that it will be clear to you. So I have represented x1 to z1 probability as p square plus q square. We obtained. Okay. So you can write this p square plus q square as p plus q whole square minus 2pq minus 2pq. Okay. P plus q whole square is, what is the sum of the probabilities? P plus q is 1. So 1 minus 2pq. So it is equal to p dash. It is equal to p dash. We are assuming like that. Okay, we are assuming it as p dash. So p plus q whole square minus 2pq. Just I have written as p plus 2q whole square minus 2pq. But this p plus q is nothing but 1. So 1 minus 2pq. So we can write it as some p dash, because it is a forward probability. Similarly, what is probability of x2 to z2? Once again, it is p square plus q square. Once again, we have represented as p plus q whole square minus 2pq, where p plus q is 1. So 1 minus 2pq, so which is p dash. Similarly, what is the probability of x1 moving z2 or x2 moving z1? It is 2pq. Let us take it as some q dash, because forward probability we are representing in the form of p, and opposite path we are representing in the form of q. Because it is a cascade, let us represent with a dash, some p dash and q dash, where p dash is p square plus q square, which you can also write it as 1 minus 2pq, and q dash you can write it as 2pq. Now with this, I think you can say that what is the channel capacity of binary cascaded channel. So for a binary cascaded channel, C is equal to 1 minus h of p dash or 1 minus h of q dash. Because for a binary symmetric channel, what is the capacity? 1 minus h of x or 1 minus h of y and represent chesam. Or 1 minus h of p or 1 minus h of q and చెప్పి represent చేశారు. But here instead of p we have 1 minus 2pq, that is p dash. So h of p dash or h of q dash. So 1 minus h of p dash is, what is the entropy of p dash or x dash, that is h of 1 minus 2pq or h of 2pq. Okay, this expression directly we represented using the binary symmetric channel. So for a binary symmetric channel having the probabilities having the probabilities P and Q, we represented as, how we represented 1 minus of or 1 plus అని చెప్పి రిప్రజెంట్ చేసాం. 1 minus of minus P log P base 2 minus 1 minus P log 1 minus P base 2 వచ్చింది మీకు. So we represented as 1 minus the corresponding entropy H of P or H of Q. But here instead of P, we have P dash, where P dash is 1 minus 2PQ. So directly I represented as C is equal to 1 minus H of P dash or 1 minus H of Q dash. Okay, this is how we evaluated the capacity of a binary cascaded channel. Okay, next channel is binary erasure channel. So we can discuss it in the tomorrow's class. And after that, we can continue with the Shannon-Hartley theorem, that is the capacity of a Gaussian channel. So any doubts in the today's class? Any doubts?